Hello, everybody. Good morning, good afternoon. Very good. All right. Welcome to our last live lecture for this course. I am very glad for you all that you have been making good progress until this point in time. I want to encourage you to leave no stone unturned to finish up the assignment for this last week, mainly the final R project, and then you will wrap up this course with a satisfactory grade. All right, very good. So let's now get started. Today we will cover a weighty subject, which is the main thrust of the materials we covered so far up to this point. Is called hypothesis testing, and we know that the descriptive statistic that we have done in the previous sections, previous modules, are that to pave the way for we come to this point. Descriptive statistic per se is not the goal. The goal is to make inferences about the population parameter, okay, about characteristics in the population parameter which are of greater interest to us. Because to have census data for population parameter is very expensive, or we don't usually have the luxury of this type of having access to this type of data. So we have to depend on sample. Therefore, we describe sample data, and in order to see if we could make some reliable estimates about the population parameter. Okay, so now I will skip the section 1, 6.1, and I'll jump to 6.4 and cover 6.5. Well, there are, as I mentioned before, there are different targets and different bullet, I call it. Okay, here in every hypothesis test we shall realize what our target is. Then based on our target, we choose our bullet. Then we can do our hypothesis testing in a correct and efficient way. Okay. Excuse me. Here we want to see first the p-value. Okay, p-value is the very, very important value. It's an index. Excuse me. I'm still a little bit under the weather. The flu now is very powerful. Sorry. Okay, so corresponding to p-value, it corresponds to an observed value of a test statistic. The p-value, or attain the significance level, is the lowest level of significance at which null hypothesis would have been rejected. In plain words, p-value shows how strong your evidence. Alpha is the tolerance level of type 1 error that you can tolerate. So, so you compare p-value with alpha. If p-value is less than alpha, that means the possible type 1 error you will have in rejecting a null hypothesis based on your sample statistic, your evidence is lower than you want to tolerate. Therefore, it's a go ahead to reject the null hypothesis. Okay. The smaller p-value is, the stronger your evidence will be from your data, from your sample. Okay, so that's why we p-value is very important. Okay, and this is how p-value is calculated, depending on what type of which tail of the test you have. If it's a lower tail test, then p-value is less than is a test statistic less than the claim less than the claim value under no, is the, let me see, p-value, yeah, p-value is that the probability that the test statistic will be less than the a test statistic from your sample statistic. Okay. First, you compute the test statistic, but then the random variable x less than that specific test statistic will be the p-value for your lower tail test. Here's a typo. Okay. Oh no. Yeah, here's a typo. Here is a higher upper level test. Okay. There's a typo here. And the two-tailed test will take the absolute value or the sum of the two tails. Okay. So this is typo: lower tail, upper tail, and so forth. Okay. Here if you look at this question, here it says, suppose the test statistic z results in a computed value of 1.58. Okay. Then p-value equal to pz greater than 1.58. So this means you find the two tail areas and sum them up, will get the p-value for a two-tailed test. If I change this to greater than 0, then you find a p-value which with z greater than 1.58. Okay, the area under the curve to the right of 1.58 will be it. Okay. All right. So this is a p-value, very important value. So you compare p-value, whether it is less than your specified alpha value, to determine whether you are comfortable to reject null hypothesis or not. Okay. Okay, so using p-value approach, you'll come to see this question. Suppose your current value is 15 and alternative hypothesis is less than 15. Then you, based on the sample statistic, we use the normal approximation. So the test statistic is 13.8 minus 15. Excuse me. Minus 15 over 4.2 divided by square root 45. So you get the z is negative 1.591, and based on the previously mentioned principle, you calculate the p-value, and p-value shows that is less than, is greater than 0 alpha. Alpha is very small here, 0.01, so we cannot reject null hypothesis, because if you reject null hypothesis, the probability that you will make type 1 error is 0.0274, which is greater than 0.01 you can tolerate. So do not reject. Okay. This is steps in the hypothesis testing. Okay, I will leave it to you to read. Then 6.4.2 says hypothesis testing for a single parameter. Yeah, that means one sample test. Okay, here we see you can see we have Z test statistic Z test statistic is T. The differences is here that for this one we have large sample size, and so we use a test statistic Z given by this. Okay, otherwise we use T to approximate it. So here's a summary of the hypothesis test. All right, what kind of test, what do we use, and so forth. All right. We have here we see the critical value approach. Critical value approach. If the Z fall in the less than critical value for a left tail test, for the there is a typo or let me see. Yeah, this is a typo. It should be greater than. This should be greater than Z greater than. Okay, you either greater than the upper tail or less than the lower tail. You either greater than the larger critical value or it's less than the smaller the negative critical value. Okay, so here's a typo again, and so there's typo here too. This should be greater than. Okay, greater than. Yeah, these are the typos that you need to be aware of. So here, let's look at the way to calculate a p-value approach. So use this to calculate the test statistic. Then you can use it to compare with the critical value, the lower one, because if you look at the alternative hypothesis is less than, so it's a lower tail test. And then so you can get the p-value is this. And now we compare with alpha 0.01, which is smaller than alpha. So that shows your data support you to reject the null hypothesis. And if you use intuition, you will see someone say, oh, okay, the average miles per car average is 18,000 miles per year, but you think it's not that high, should be lower than that, and the sample size is 17,463. So, and the standard deviation is large. Anyway, this is a little bit hard to tell based on this information, but I believe it's because deviation is large. Yeah, it's hard to tell from these numbers. Sometimes you can tell from the numbers which whether you can reject it or not immediately without calculating. Okay, here is a case when mu equal to n is small. N is small, so we cannot use the normal approximation. Therefore, we have to use T. Yeah. Okay, and also but even for T, we have to check the normality because T test is based on the assumption of the normal distribution. Because of the small sample size and less than 30, we choose t-test. Even given a t-test, we still want to make sure that the population from which it is drawn follows the normal distribution. Now in this question, it's similar. Okay. All right, now we see the one population parameter, mu-s parameter. Now let's look at another parameter, which is population proportion. Okay, population proportion. How do we use proportion as a parameter to test to test the hypothesis for it? Okay, here we use P to denote population proportion, and then this is the formula to which we can use to calculate the test statistic. Okay. So, and the rest of it is just the same. Now, here we come to see the summary of hypothesis test for the variance sigma square. Sigma square from the one population parameter, sigma square, and the Klein value for sigma square is sigma 0 square, and so forth. And the test statistic calculated by this. The reason why for this is that on the right hand side, this follows a chi-square distribution. Okay, chi-square distribution. And the test statistic is calculated by plugging sigma square as sigma square is equal to sigma 0 square on the null hypothesis, and then you plug in S square on sample. So in this way, you are actually comparing the sample variance with Klein, the population variance. Okay, and see whether it's large and large enough for you to reject the null hypothesis, or whether it's small to not reject it. Well, become test statistic for us to compare with the critical values. So here, if you read the question, you will see that we are to compare variance of the cholesterol level and out of 25 adults. And currently, a physician claimed that the variance is 100, but we want to make sure that's true. So we do conduct the hypothesis test. We assume that it is smaller than that. So the alternative hypothesis always put the hypothesis of interest to us on the alternative hypothesis. Okay, so given all the information in the question, we can establish a rejection region must be on the left-hand side, which is consistent with the alternative hypothesis. Okay, so then you can calculate the test statistic and compare it with the and then compare it with the rejection region, and therefore you can conclude that it's not in the rejection region, so do not reject. Yeah, that means it's not small enough for you to say that the physician's claim that the variance is 100 is not true. Okay, you have no evidence to support you saying that. Okay, so this is one sample case. In summary, you have what? Mu as target, P as target, sigma square as target. And mu is a target. You use X bar as a bullet to shoot for it to be the test statistic. Okay. And then if P is the target, then you use P hat. If sigma square is the target, then sigma S square is a bullet. Okay, so the different target, you have different bullet, and then based on the different values, which is sample statistic, you can calculate, calculate it to be the test statistic. Then you compare test statistics to see whether it falls within the rejection region, and you get the conclusion whether you should reject the null hypothesis or do not reject the null hypothesis. Okay. All right. Now here we come to two samples. For the two sample hypothesis test, let's first look at the independent samples. Two samples are independent, satisfying this criteria. So in this case, we shall consider following three cases in testing hypothesis. When sigma 1 square and sigma 2 square are known, then when they are unknown and both sample sizes are big. When they are both unknown and sample sizes are both small. And then in the third case, in case 3, we have the following two possibilities, that they are equal or not equal. Okay. Yeah. So these cases to consider. And here we see the comparison of two population means. We say that is equal to or less than or greater than, they are equal to certain constant, D0. D0 can be 0 or any other values in the real life. An alternative hypothesis means it can be right tail, upper tail, lower tail, or two-tailed. Okay. So the test statistic is on the denominator. We see the differences between the sample differences and the population differences. So by doing this subtraction in the numerator, we see that we are to find the differences of our estimator with our target. Okay, and then divided by the merged variance, merged standard deviation. Okay, so that become our test statistic, and if our test statistic is far away from the center to the rejection region, then we should reject the null hypothesis. Okay, here is an example of salary, and you use the you use two data, null hypothesis and alternative hypothesis. Okay, this is right tail test. So, and D0 is 0. Okay, so plug-in the formula, and because both N1 and N2 are large, so you use S1, S2 instead, and then still use Z to approximate the result. And your result shows that your test statistic is 6.7, but that is greater than 1.645, which is greater than your critical value and fall in the rejection region, so you reject the null hypothesis. Okay. And here we see that there's a note here. Even though sigma 1, sigma 2 are unknown, okay, we don't have sigma 1, sigma 2, but squares, but because n1 greater than 30, n2 greater than 30, so we could replace them, sigma 1 squared, sigma 2 squared, by the respective sample variances. Yeah. And we are assuming that the series of the male and female are sampled independently of each other. Yeah, because we reject null hypothesis and conclude the alternative hypothesis, that means mu1 greater than mu2. And that means their theory are different. Okay, now we compare two population means, small sample case. In this case, since sample sizes are small, and so we have to do it in different way by by merging the sample pooled variance, pooled standard deviation in this way. And then when we plug in the pooled sample variance into this formula, we shall get the test statistic, and then compare test statistic with the critical values, and we shall be able to draw good conclusion. And here we can see this is how it works. So, but this is what when the two population variance are equal. Now let's consider when two population variances are unequal. So they cannot be assumed to be equal. We cannot assume them to be equal. Okay, so we have to do it this way. But when we are calculating the t critical value of t, we need to take this into consideration, which is we adjust the degree of freedom according to this formula by Smith, Setters, Schwartz. Okay, then you will get with this new degree of freedom, you will be able to calculate a new t value, test statistic, critical value. Okay, let's look at this example. Obviously, they all look like similar, but our sample sizes are small. When they are small, we let me see. Sample size are small, and we merge them. So this is according to this case. Okay, this case. When the two population variances are equal. Let's see, we should see something like that here. Populations are equal, right? That's why we use the merge the population's standard deviation, pool the standard deviation. Okay, but if their population means okay, then in this the two, yeah, they are not equal. No homogeneity assumption is made. So we use the Shady-Swaty formula and this to conduct a t-test. You should be able to use, yeah. You are in your R project. You should compare it with your output and see how your manual calculation result match with your our results. Okay. Now this is pooled, okay, because we assume that they have equal variances, but then B, we have to look at the assuming inequality of population variances. So in this question, you try the two different approaches. I mean different assumptions. So you see how different they are in their results. Now, not only population can have two population parameters to consider together. We also have the two population proportions combined to consider to be compared. So this is you can see the similarity between one population's proportion and two population proportion differences. Okay, so this is the case, but then you have to compare, see if NP greater than 5 or N1 Q1 greater than 5, because this is the criteria. Because if they are not satisfied, then they will be too skewed to be well approximated by normal distribution. Okay, now here is an example. Yeah, you just read the question, follow this example, you shall be able to get the correct result. Yeah, every time when you practice, work on the question, watch out the assumptions, and so that you may choose the appropriate methods to handle that question. Okay, and then we have already seen chapter 4. Then we also seen the one population variance, but here we have two population variances. So in fact, we are comparing whether they are equal or not. Actually, this is you can say this is a pre-test. Previously mentioned that the way you calculate test statistic, the way you calculate the critical value will differ accordingly. So usually we do a test for equality of variances, and then we decide which method to use. Either we merge the standard deviation, or we do not merge. Okay. All right. So using F as a test. This is a test statistic because the ratio of two sample variances follows the F distribution. Yeah. All right. Okay. So this is the chi-square test, and so if given a question like this, and we will test whether this is okay, which we shall conclude. Then we use the test for two-tailed F test, and then compare whether this value of F for this value of F is greater than the upper bound or lower than the lower bound, to determine whether they are equal or not. Okay, this is your criteria. Lastly, we have dependent samples. Dependent samples are samples that are the observations made on the same subject during a pre or post test or similar scenarios. So what we do is to find the difference, which is D bar of the observation. For example, there are 20 students and 30 students, to be a bigger sample, and then they took a test before tutoring and after tutoring, same level of difficulty. Then compare the two scores by subtracting one from the other because they are made on the same person. So in this case, we shall use the difference of two means for the test. Okay, this is detail. So in the end, this shall be similar to the mean one sample population proportion test. One sample population mean test. Okay, and because of the small sample size, we and then the poor SD, we will assume we cannot use Z, but we have to use T. Okay, yeah, these are formula. Okay, so this is I think let me see. Okay, yeah. My time for recording is about to end. I think this is should be a good point to stop. I cover most of the content already. To recap, you please we have one population parameter from one sample, and then we have population parameter test, hypothesis test for two samples, and then okay, one sample and two samples, and you have different targets. You have mu as target, p as target, and sigma square as target. You also have mu1 minus mu2 as target, and p1 minus p2 as target, or sigma 1 square equal to sigma 2 square as target. You have different targets, different assumptions, different conditions you have to consider separately. So when you work on questions, you pay attention to the details, you find the appropriate test for the test accordingly. Okay. And then you please make sure you finish all your assignments, turn them in before the last day of class. That's a hard deadline for everything. So far you have been doing so good. So far so good, pretty good. I'm happy for you all. So I hope that you don't leave no stone unturned until you ace the class and wrap the class up with the satisfactory grade, and then move on to the second course. Okay. I look forward to meeting all you happy entering the second course happily. Okay. Yeah, I will let you listen to the recording and think about it. If you have any questions, welcome to post questions on the discussion forum. Okay. All right. Okay. I think that's it. See you next time. All right.